So today I'm planning to cover section 13.3 on the dot product, but I'm going to take a little bit of a detour to get there, so I hope you'll bear with me. The first stage of that detour is to remind you about the law of cosines. So this is something you presumably learned in pre-calc or trigonometry, but it tends to be one of the elements of trigonometry that gets dropped when people are doing that course. And it's also probably the hardest thing to remember. Basically, you should think about the law of cosines as being a modification of the Pythagorean theorem. So you take, let's call it c squared equals capital A squared plus b squared. And you make a modification to it to deal with a scenario where you're not in a right triangle. If you're not in a right triangle, you don't have this identity, right? So the modification is this. You need to subtract off 2 times the product of A and B and the cosine of the angle that lies in between, well, that lies where the right angle would lie if it was indeed a right angle. So there's, let's call it theta here. So if you had this guy with a right angle in it, C would be the hypotenuse and A is this side and B is that side. But if you don't have a right angle there, we still call these guys C, and this one's A, and this one's B, and that angle that we just changed, that's no longer 90 degrees, that's where theta is. Okay. So I don't know if people remember this. I think it's got a nice proof. There's a couple of nice proofs of it, so I wanted to quickly go through that. And then we'll proceed on to see why is this relevant to figuring out how the dot product works in R3. So I made a copy of this triangle down below at a slightly bigger scale so that we can see things better on it. The main idea is this. We're going to drop a perpendicular from the apex of that triangle, the way it's drawn. So that'll be 90 degrees at the bottom. And we are going to analyze the two pieces of the bottom edge there that this dropping of the perpendicular has created for us. There's a piece right here that is related to angle theta, and well, we've got the hypotenuse of the triangle that theta is part of now, a right triangle. So this part is the side adjacent to theta, and that's the hypotenuse. That makes this guy b times cos theta. If you divide this by the hypotenuse, you should get cos theta, right? So the other piece of that triangle we're going to need is up right here, and the height of this line, this is b times the sine of theta. Now, that's using this one right triangle on that side. We'll now shift our attention to the other triangle on the left. And the sides of it are, one of them is this b sine theta, so these two triangles share that edge. But the other side is the difference between A and b cos theta. So I'm going to erase A there for a sec. The piece that I'm talking about is from here to there, and that is A minus b cos theta. Now, those two things are part of a right triangle which has side C in it, so the Pythagorean theorem can be invoked. And I think I'll just try to keep our diagram there so we can follow it while we do some algebra. The Pythagorean theorem on this left side triangle would say that c squared is equal to the sum of the squares of the other sides. So we have a minus b cos theta squared plus b sine theta squared. Alright, so just a bit of work to do. I'll have to FOIL rule this side out, and you'll get a squared minus 2ab cos theta, because outer and outer times outer and inner times inner are both the same. And then finally there's a plus b squared cos squared theta. I hope I've got room for this piece still. That'll be b squared sine squared theta. Right, so you probably spot the Pythagorean identity right in there. If you factor out the b squared, you'll have cos squared plus sine squared. So this is a squared minus 2ab cos theta plus b squared. I could take another step, I suppose, to factor out that b squared and see that cos squared plus sine squared add to 1, but I think you guys are good enough to follow that. So yeah, what do we have here? We've produced from the left side and the right side of the law of cosines as I wrote it down. Just rearrange. C squared is equal to a squared plus b squared minus 2ab cos theta. All very cool, but why is that of use if we're talking about, you know, the dot product in R3? Why don't we put some coordinates on things? Yeah, so this is what I mean by putting coordinates on things. Think about some vectors. We've got just two arbitrary vectors. They're in 3 dimensions, but they could be done in 2 dimensions as well. I mean, obviously the drawing I'm doing here is 2-dimensional, but I want you to think of those as lying just somewhere off in 3-dimensional space, pointing in arbitrary directions. There's I've put coordinates on them in the textbook. If you look through this, they call them U1, U2, U3. I like ABC better. It's just I don't want to have to write all these subscripts X, Y, and Z rather than V1, V2, V3. But you should be able to follow in either presentation. Right, so that's 2 sides of a triangle. What's the third side? It's a vector that goes from the tip of U to the tip of V. Now, I could go the other way too. So, in fact, let me think about which one is this. If I do U minus V, which direction does that go? That's like adding to U the negative of V. Negative of V is this way, plus U, that would end up about here. I think that's the opposite direction. All right, so if I orient this guy with the tip at that way, is that U minus V? Think about it as, yeah, well, it is. Just slide it over here and you'd see that it's U minus V. There's a parallelogram out here that goes off the edge of my board. All right, so U minus V, what's its coordinates? A minus X, B minus Y, and C minus Z. And these 3 things, these 3 vectors, actually are the coordinates of, you know, you may think of them as points in R3, points in 3-dimensional space. They're also the sides of a triangle. Just forget about that they're directed. How long is this guy? How long is that guy? And how long is that guy? So what are the lengths of these vectors? Now, I don't know if we got to talking about the distance formula and the lengths of vectors in the intro to vectors section. But You know, it's just really easy. How long is a vector? Well, it's the distance between its initial point and its terminal point, which is you know, something that's broken up into three components there. So to get the length of a vector, you just square root of the sum of the squares of those numbers. So if you haven't seen this before, it may seem a little strange, but we use absolute values for that idea. Put the vector inside absolute values means how big is it? What's the magnitude of the vector? And so for us here, the magnitude of u would be the square root of a squared plus b squared plus c squared. Similarly, the magnitude of v, that is the square root of x squared plus y squared plus z squared. And then lastly, the magnitude of u minus v, this is the hard one. That's the square root of the sum of the squares of its components. So what is that? It is the square root. It's going to be a big square root. I hope I don't need all of that space, but I've got it there just in case. A minus x squared plus b minus y squared plus c minus e squared. I practically did need all of that square root, but let's get rid of that little stub on the end. All right, so these three numbers satisfy the law of cosines, and we'll use the angle theta is going to be what's right in here. So the angle theta was across from the edge you're thinking of as filling the hypotenuse role, right? So this guy would be our C, and I don't care which you call which. Think of that one as A and this one as B. Right, so let's write down the law of cosines with these things filling the roles we're talking about. I was about to erase everything, and then I realized that it might be smart for us to see the substitutions a little more better if I could show you which things we're doing. So here's a copy of the Pythagorean, excuse me, not the Pythagorean theorem, but the law of cosines. The pieces here are going to be that difference between the vectors, that's our C, and we were using A as the first of the vectors and B is the second of the, or rather the lengths of those things. So right, when we get C squared, it'll be the sum of the squares of these differences, because the squaring undoes the square rooting, right? So we'll have A minus x squared plus B minus y squared plus C minus z squared. A squared and B squared both have a similar simplification. You're squaring something that's got a square root on it. So you get A squared plus B squared plus C squared from the one. And you get x squared plus y squared plus z squared from the other. And then we get something that I'm just going to call it 2 times an unknown. This is 2 times this quantity, AB cos theta. So let's just call it 2 times question mark. Right? Because what I want to do is show you that question mark turns out to be something really quite simple. All right, so we'll leave it like this, but we're going to solve it for this question mark thing. What would I need to do to solve it for a question mark? I would have to add 2 times question mark to the other side. I guess I can divide by 2 first, and then move the other stuff the other way. So let's see if I can just do this algebra all at once. The unknown thing, the question mark, should be equal to 1/2 of these things are staying on the side, so it's the negative of this guy that needs to be subtracted. Yeah, need to subtract. All right, so let me write it. It's going to be a squared plus b squared plus c squared plus x squared plus y squared plus z squared. I guess I'm going to have to break the line. Minus a minus x squared plus b minus x squared plus c minus, oh, did I do that wrong? No, I did. That's supposed to be a y. The positions in the sequences A, B, C, and X, Y, Z need to match. C minus C squared. So now I can get rid of this stuff that's underneath and continue working downward. I think mostly we just need to do 3 applications of the FOIL rule there. Oh wait, do I have a mismatch in parentheses? Got an open one there that doesn't get closed. Yay! All right, so our unknown thing, what I'm after is 1/2 of, I guess I'm just going to have to copy that first bit. So, and since everything is added, the parentheses are really unnecessary there. A squared plus b squared plus c squared plus x squared plus y squared plus z squared. And then look what else we're going to get. Well, let's FOIL rule these things out. You'll get a squared minus 2ax plus x squared. This one is going to give you b squared minus 2by plus y squared. Yeah. And finally, the last one is going to be c squared minus 2cz plus z squared. And one more parenthesis to match the initial one. You see what survives? See, there's an a squared, but down here we're subtracting an a squared. B squared, we're subtracting b squared. C squared, subtracting c squared. X squared, there's x squared. Y squared, we're subtracting that somewhere too. Here it is. And z squared. So the only things that remain are minus 2cz, minus 2by, and minus 2ax. And those all have a minus sign associated with them. And a 1/2, right? So that's really just the products of corresponding terms in the thing. That is the question mark guy that I guess I can get rid of this now. The question mark that I identified, that's just equal to ax plus by plus cz. Oops. ax plus by plus cz. But what else is it equal to? It's also equal to a times b times the cosine of theta. So these two things, since they're equal to the same thing, must be equal to one another. And what was a? That's the length of the vector whose components were a, b, c. And what was b? That's the length of the other vector whose components were x, y, z. In terms of the vectors I just talked about, this is length of u times the length of v times the cosine of the angle between them, which is kind of a freak of nature. What it says is there's this simple thing you can do with the components, multiply corresponding components and add, and you get this computation, the product of the lengths of the things times the cosine of the angle between them. Our textbook uses this thing as the definition of what the dot product is. I personally believe this thing is the dot product, but it doesn't matter because they're the same. It's just a matter of an emphasis. So what is the dot product useful for? The dot product will tell you when two vectors are actually perpendicular to each other. That's one of its biggest uses. It becomes a test for orthogonality. U dot V provides a quick test to see if two vectors are perpendicular. I said perpendicular. The other way to say it is orthogonal. I kind of like orthogonal in this context. And so if I've got two vectors that I think are perpendicular to one another, orthogonal to one another, but I'm not totally sure on it, I can just do this little computation and find out. All right, now I have a slightly difficult job ahead of me here. I have to try to draw for you some vectors in 3 dimensions on a flat board. And thinking about that, it made me realize there was a small thing that was left out of the last lecture, which I should probably mention. When you're in a 3-dimensional coordinate system, 3 different axes, there's a funny choice that doesn't show up when you're in 2D, so we're not used to thinking about this. But right now, I'm using my right hand with the thumb pointing upward. I guess my index finger pointing in the X direction. My other finger pointing in the, what do you call it? Middle finger. Oh yeah. Pointing away from you guys into the board. So this is actually the normal orientation one does for drawing things in 3 dimensions on a blackboard. That is, have Z go perpendicularly upward, have X head off to the right like it always does, but Y goes away from you into the board. All right, so that's the idea. X that way, Z this way, and Y fading into the distance. Maybe if I make the arrow really tiny back there, does it look like that it's faded into the distance? That's a tiny Y. I don't think that's helping. So I'm going to make the Y visible, but that's the idea, right? So X and Z in the usual X and Y positions, but Y is now going away from us. And I made that whole thing by gesturing with my right hand. Notice that if I did the same thing with my left hand, I would have a different convention. X and Z would still be where they are, but Y would be coming out of the board. And then we would have what's known as a left-handed system. Watch out for that. In certain computations, left-handed systems will not work, or they won't work the way one is expecting. So if, for instance, in a vector computation, you come up with an answer for some quantity that you know is positive and it's negative, your answer is negative, that's one of the places to look. Did you accidentally produce a left-handed system when you were putting coordinates on things? There's multiple ways of thinking about this. I use the holding your fingers like this, with Z as your thumb and X as your forefinger, middle finger is Y. Some people talk about point your fingers of your right hand along the X-axis, curl them so that they curl towards the Y-axis, and if you do that, your thumb better be pointing up. If you try that with your left hand, you have to do this and curl towards the Y, and you see how my thumb ends up downward. So it's just a function of, your hands are mirror images of one another, and so trying to get the fingers of your other hand to bend in a way that they don't. I guess you can almost do it in my version of things. If you get a lot of flexibility on your middle finger, you can poke it around, but it hurts. So this way is not painful and gets you the idea. All right, so here's our XYZ system. I'm going to draw you a vector that should be thought of as pointing out sort of the average of these coordinate axes. It's pointing out into the first octant, it's known as. So this is the vector 1, 1, 1. It's got components, all three components are equal. And then I am going to have x and z both be 1, but have y be -2. So this vector might not look like it, but it's coming towards us. Here, I'll try to make it look like it's coming towards us. Does that look like the tip of a... No, it doesn't look like anything. Just imagine it's coming towards us, all right? Anyway, that's the vector 1, -2, 1. Now, it doesn't look like they're perpendicular, right? If you look at that angle in there, well, it's close, but that's just an artifact of the particular angle we're seeing them from. But I can do this dot product calculation real fast and say, oh yeah, they are perpendicular. How about that? So what is that dot product? I would take, let's just write them next to each other first. 1, 1, 1, dotted with 1, -2, 1. And what you're going to do is multiply corresponding things and then add up as you go along, right? So it'll be 1 times 1, 1 times -2, and 1 times 1. I'm going to write it out this once, but ordinarily I just trace through the things and multiply and keep a running tally, and you can work that out. Right. And of course that's 0, right? So the fact that this comes out 0 means that the length of the two vectors, well, what is the length of that vector? That's not so hard to do. It's the square root of 1 squared plus 1 squared plus 1 squared, or root 3. And the length of the other vector, it's 1 squared plus, that's 1 plus 4 plus 1, that's 6 under the square root. And the cosine of the angle. So we've got the product of these two non-zero numbers, and that cosine of the angle equals 0. It must be that the cosine of the angle is equal to 0. So what does that tell you about the angle? It must be 90 degrees. Or pi over 2 radians. Proved orthogonality by using the dot product. So what I have here is my very best attempt at drawing a perfect cube centered at the origin. I worked diligently on this, but it's an x. Oops, I forgot to label y. The y is that little stubby one because I didn't want it to interfere with the rest of the drawing. X, y, and z in the usual orientations with y going away from us into the board. The coordinates of this point in the upper right-hand corner, those are 1, 1, 1. If I give it as a point, I guess I can write it as a point, x, 1, 1, 1. X, y, and z are all 1s. If I think of it as a vector that goes out there, then I would just change the braces to angle braces. I should probably say coordinate vector. Drop straight down from that point to here. What did you do? You would have had to go from, well, x and y are the same. You're still in the same position relative to the xy plane, but you changed z to a negative value. So this would be 1, 1, minus 1. Do you think those vectors are perpendicular? Well, I mean, it kind of looks like it. Maybe not quite, I don't know. But a quick computation with dot products gets you a dot product of 1. It's not 0, so they're not orthogonal. Those are not perpendicular vectors. Let's see, what if I go from this point forward towards the camera? That's changing the sign of the y coordinate. The y coordinate was 1. If I move in this direction away from the opposite of into the board, out of the board, you're going to get the same, my marker's dying, give a different one. The same x and z coordinates, but the y will be negative. So minus signs. Another point, another one of these points that's kind of often talked about is the one that's dead opposite to 1, 1, 1. If I make y negative, x negative, and z negative, I end up at this point down here, sometimes called the antipode. Minus 1, minus 1, minus 1. In the geography of the Earth, the antipode is a point opposite from you on the surface of the Earth. I think for us it's somewhere around New Zealand. Yes, I could fill in the rest of them, but they're boring, right? Their coordinates are always plus and minus ones. One thing that's not boring I want to show you is what you get if you sort of take every other corner of the cube. So maybe start with this 1, 1, 1, but then don't take these guys and don't take that one. Take this guy, he's a sort of a 2 away from the 1, 1, 1, and this guy, 2 away from the 1, 1, 1. And there's a third one, which is antipodal to this one. It would be in the back. I forgot to draw the back. Wow, I was bragging about how careful I was about drawing this cube, but I didn't even draw the parts that go in the back. Sorry. Well, we should drop straight down from there, and we should run straight over from here. That's the back of the cube, that corner. That guy's coordinates are, oh, what are they? Let's see, x would be negative, we're on the left side. Z would be negative, but y, that's in the back, so it's into the board. It's got a positive y coordinate. And that's one of the ones that I want to circle in red as well. Cool. So I guess I've only got one last one to do to get coordinates on. So let's figure out what this fourth red point's coordinates are. In the x direction, we're on the minus side. In the z direction, we're on the plus. In the y, we're close to us as opposed to far away from us. So farther away is positive y's. This is a negative y. So what did I just say? Negative x, negative y, positive z. Now, a quick way to spot these points that we've just calculated or just found and pointed out to you is that they're the ones that have an even number of minus signs. See how this one has 3 minus signs? Don't put it in. That one has 1 minus sign. That's odd. Don't put it in. This one back here, I don't know what it is, but it's odd. Don't put it in. This one has no minus signs. That's fine. It makes it even. So those are good. So we've picked out, amongst the vectors who have plus and minus ones as their coordinates, we've picked out the ones that have an even number of minus signs. And why did I do that? Because the vectors that go out to those things are a very interesting set of vectors. Those vectors form the 4 points of a thing called a caltrop. It's seen even in modern military uses because it's 4 vectors that point all of them the same angle away from one another. And that means that it always forms a tripod with any 3 of them. So if you laid that thing flat on the ground, it would look like this. Those 3 points would lie on the ground, and the third one would be sticking up. And if you make this thing out of a big hunk of reinforced steel, it becomes a tank trap. No matter how it's laid down, it has a spike that goes up. People used to make them smaller versions, maybe 3 or 4 inches across, are great at completely disabling cavalry because a horse that steps on that thing isn't going anywhere else. Yeah, so used in warfare, but also this geometry has its place in the natural world. The things with the angle between them all the same, all these angles in between the lobes of this thing, I don't know how many angles there are. Actually, I do, there's 6. There's 6 different places where you could calculate angles. Those angles all being the same is what happens if these things are points on something that have the same charge. So suppose these were all negative charged things. and this thing in the center had a positive charge. So these things, the negative things are attracted to the positive charge. They want to stay near each other, near that thing, but they want to stay far apart from one another. What atom, or what molecule, or yeah, I guess atom am I thinking about right now? That's the way carbon works. The carbon atom has this structure where there are lobes of negatively charged electrons that, well, the last one's kind of hard to draw, that form these regions through which you may get attached to other carbon atoms or other atoms in general, and they're always 120 degrees. Oh no, it's not 120 degrees. That was a good guess, but there's some angle between them. It's all the same. Now it turns out to be not quite as simple physically as what I just described. If it really depended on these all having negative charge and sort of repelling one another, then another atom, like say oxygen or nitrogen, with different numbers of electrons in its shells, would get a different geometry. They don't. All the atoms that have these sort of bonds in the, I think that's the p orbital, they always form these particular angles that are associated with the carbon molecule. So for instance, when you see the H2O formula, I don't know if people have ever thought about this. It's normally thought of, you've got the oxygen in the middle, and you've got hydrogen this way, and hydrogen that way. But that's not right. In fact, the bonds on the oxygen are like these guys. They come out at this funny angle that has to do with the geometry of caltrops, or points on a square, if you like. And so H2O does not look like that. It doesn't really look like that. It looks more like, here's the way chemists probably prefer to think of it. It's a big sphere with two little spheres kind of globbed onto it. But those two little spheres are closer together. They're not across from one another. And that makes the molecule polar. It means it's got one end that's positively charged and another end that's negatively charged. That's really important, because that's what makes water water. If without the polarity of the water molecule, water wouldn't be the wonderful solvent that it is, and probably wouldn't provide a basis for life. So it's kind of important that this weird angle shows up the way it does. So what's our job now? Let's figure out what that angle is. Okay. I need two of these vectors, so I'm going to take the 1, 1, 1 and the 1, minus 1, minus 1, and I'm going to form their dot product. All right, 1, 1, 1 was one of the vectors I mentioned, and anything else that has an even number of minus signs, I don't really care. So how about minus 1, minus 1, 1, two minus signs in it. The dot product there is minus 1 plus minus 1, that's minus 2, plus plus 1. All right, it equals to minus 1. But that's also equal to the length of the one thing. I'm just going to write it out first. Length of 1, 1, 1 times the length of the other one, minus 1, minus 1, 1, times the cosine of the angle. And that's the thing we're really interested in figuring out. Now, what is the length of this? It's the square root of 1 squared plus 1 squared plus 1 squared. It's root 3. And this, because you're squaring and then adding, these minus signs really have no effect. That's also root 3. So what we got there is root 3 times root 3 times the cosine of theta. Well, what did I say that was? That was minus 1. So the cosine of theta is negative 1/3. I got a calculator, and if I take the inverse cosine of negative 1/3, you find out that theta is 1.91. That's radians. About 2 radians, so I always think of a radian as roughly 60 degrees, so it's close to 120, but it's not really. Let's do this in degrees, just because I have a better feeling for degrees sometimes. Just put it into Greek mode and took the cosine inverse of negative 1/3, and it's 109.47 degrees. So that actually is the angle that you'll find most naturally in organic matter, 109.5 degrees. I'll make one small comment on this. The oxygen atom at the center of water has that perfect 109.5 degrees angle on its potential sites for bonding. But as I mentioned, the hydrogen atoms that are at the end of those bonds, they develop the same charge. They are electron donors. The oxygen has a outer shell that kind of has places in it for electrons, and the hydrogens have an outer shell that's only got one electron in it. They tend to make the electron spend more time down by the oxygen than it does by them. So these guys become positively charged, and the central oxygen is a little bit more negative than they are. So that means that there is this effect of things that are of like charge wanting to separate. And what happens is this bond actually just bends out a little bit. And so the angle is not exactly 109.5. It's influenced by the repulsion of the hydrogens by one another, but not very much, a couple of degrees. So that is slightly more open than 109.5. You can look up the angle on the bond on hydrogen on water if you like, and get the exact number. It's not very much different from the theoretical number that comes just from geometry. All right, so speaking of theory, let's talk a little bit about, we've seen some of the ways that you might use the dot product. One is checking for orthogonality. The other is actually figuring out the angle between two vectors. There's another use that we can put it to, but before we jump to that, I want to give you some theoretical things. And basically, I want you to see how the algebra of dot products works out. If I've got two vectors, u and v, and I take their dot product, of course, that's going to be the length of the one times the length of the other times the cosine of the angle between them. None of which depends on which one I think of as the first vector or the second vector. So isn't this just patently obvious that u dot v is equal to v dot u? I think that just comes from thinking about the geometry of one of the ways to calculate the dot product. So this is the commutative law, and yeah, dot products obey it. We tend to mostly think our operations obey the commutative law. What difference could doing things in another order could that possibly matter? And it turns out, yes, it does. The thing we're going to be doing on Tuesday, the cross product, does not commute. In fact, it's the opposite of commutative. It's an anti-commutative product. But dot products work that way. They commute. What else do we know about them? If I make one vector slightly longer, so maybe multiply vector u by a quantity c, and then do the dot product of it with v. Well, I could make, instead of making u longer, I could make v longer, and it would have the same effect. Let me think about this. U dotted with cv. Why would those be the same? Well, think of it this way. You changed the magnitude of u. You stretched u by a factor of c. So the product, u times v, has u multiplied by something times v. That is, what I'm trying to say is the product of their magnitudes is, on the one hand, turning into scaling up u and multiplying it by v. And on the other hand, turning it into leaving u fixed and scaling up v and doing the product. But do you see that these things are the same? And certainly the cosine of the angle between them doesn't change if you just stretch one of the vectors, right? The direction of the vectors is what tells you what the angle between them is. So these two things are equal. which means that these two things are equal. The products of the magnitudes are the same, the angle between them, and hence its cosine is the same. Doing this thing where you either put C on U or put C on V it's immaterial. You can scale one or the other. You can't scale. I have an issue. In our textbook, they call this the associative property. And the problem with that is associativity is a property that an operation may have or may not have. But this thing that we're looking at is not one operation. You see, those dots right there are dot products of vectors. The thing that I haven't got a dot for, but where C is multiplying V, or where C is multiplying U, that's not the dot product of vectors. That's the scalar product. You're just multiplying U by a real number. So we've got real multiplication of a vector, dot product of a vector equals dot product of vector and real multiplication. And also, the associative property keeps the things. I should show you what associativity really looks like before I just confuse you about this. Associativity normally is three numbers, A, B, and C, writing alpha, beta, and gamma. You can either parenthesize them like that, or you could keep them in the same order and parenthesize it like that. That is, do the first two and then the third, or the first with the product of the second and third. And that's associativity. Each of these multiplications is the same operation, and we're just changing where the parentheses are. Here we're not only changing where the parentheses are, but we're moving the C over from in front of U to in between U and V. So calling that the associative property is strange, but I guess maybe we'll call it that just to have a name for it, but it's really slightly different from associativity. Fine. The last property that we're going to look at, which is not geometrically evident, is this. If you have three vectors and you're forming the dot product of one with the sum of the other two, so if this was ordinary multiplication and that was ordinary addition, we'd have a distributive law. And the thing we're going to see is that, in fact, that does happen here too. You can distribute, but just recognize that this is something new. We're distributing dot product, scalar product, over vector addition. So it's not the old-fashioned distributive law. It just looks like it. That's distributive. I'm just going to abbreviate it because I'm running out of space. So this one, I think we'd better argue why it's the case. Is this a better marker? Yeah, that's good and sharp. So I'm going to write coordinates for all of these things, and we're going to do not the geometric thing with the cosine of the angle and their lengths, just the raw multiply and add operations. So if we're seeing U is U1, U2, U3, and I'm dotting it with the sum of V1, V2, and V3 added to W1, W2, and W3. So that's what's the left-hand side. Now, can we say what that equals to? Sure, it's gonna be, let's do the addition first. So we'll have U1, U2, U3 out front. No change to that part, but let's create the vector where we add those guys. It's V1 plus W1 in the 1 position, V2 plus W2 in the 2, and V3 plus W3 in the 3rd position. right, it's ugly, but I can do the dot product now. Take the corresponding components and multiply and then keep a running tally of all that. So what do we get? It's U1 times V1 plus W1 plus U2 times, what is that one, the middle guy, V2 and W2 plus U3, I'm sorry, I'm probably blocking the board now, times V3 plus W3. Let me just take a second here to harp on something. I often see people doing this bit, doing a scalar product, the dot product of things, and then putting angle braces around it. Because you're thinking, well, it's a vector. So, there's vector stuff going on. But that's why this thing is called the scalar product. You just get a number out of it. So this is all just a number. No angle braces anywhere in it. All right? Don't do that to me, because it makes me sad. It makes me think that I didn't get across to you if you do that. No vectors, symbols in your scalar products. They should just look like big ugly computations with real numbers. Yay. I want to show you that that's the same as this. So I'm going to try to save this and just write from the top of the board down to here. If you notice, what I did was start with the left-hand side, right? And we're basically trying to turn it into the right-hand side. And these things, like I just emphasized, these are real numbers, right? These are operations with real numbers. That thing is dot product, and that thing is vector addition, right? Dot product, vector addition, another dot product. But that dot, that's multiplying regular real numbers, and that's adding regular real numbers. Here, the distributive law does hold. So the thing I got on this bottom line, you can distribute. So you get U1 V1 plus U1 W1 plus U2 V2 plus U2 W2 plus U3 V3 plus U3 W3. One, two, three, four, five, 6 numbers all multiplied together, and I'm hoping it looks like this: U dotted with V and U dotted with W. If I'm going to achieve that, let's pull all the things that involve V together. That is, U1 and V1, U2 and V2, U3 and V3. Those are all the guys that involve V. We'll put them up first and group them. These are still real numbers, so I can reassociate it any way I like, put in parentheses any way I like. The things involving W are, let's see, that's the first one, U1, W1. No, that's a V. There's W. U2, W2, and the last one is U3, W3. And perhaps you spot what these things are equal to. This has U, U, U in the 1, 2, 3, and V, 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 1, 2, 3. That's U dot V. And the other piece is U dot W. So I probably, when I first wrote this down, should have written a question mark there, because what we've done is take the first one, the left side, say what it's equal to in coordinates, do operations, keep going, do the manipulations that we could, just had to recommute and distribute it and all those things, but we ended up writing it as u dot v plus u dot w. So if this was a linear presentation, I would be saying, therefore, u times v plus w is uv plus uw. So that's an example of an operation in a new context, getting one of the properties of a more familiar operation. You see, what really happened here is that we could distribute these real products over real sums. And that kind of thing is known as inheritance. The vector dot product and the vector addition inherit distributivity from the real number properties of distributivity and commutativity. Okay, so the next situation I want us to compute something in is best illustrated by an example. A lot of times you have some object that's constrained to move along a linear track, but you can't pull it from the track. Rather, you have to be off at an angle. So if I was pulling on that ring at this angle, it'll move down the track. But there's really, I don't know, there's two different components to the way the forces are acting. And one component, in the way I'm doing it right now, I'm tending to lift the thing up in the air, right, which reduces its friction on the track and makes it slide and jumps. The other is something I'm pulling it along the track there with that. And the two of those things, well, they interact. But if I do it more towards you, here I'll have the sliding is not being affected by the angle that I'm pulling at. And even though I'm pulling at a fairly, pretty huge angle to the track, the thing moves along. We'd like to figure out how forces work like that. When you're moving something along a track and a force is being applied at an angle, the actual force is the component of that force vector that's in the direction of the track. Well, that's what we need to figure out. Okay, let me make a diagram, try to illustrate the thing I was just showing you. Suppose you have a track. You think of it a train track or a canal or something, and the thing that's pulling an object along that track has to do so at an angle. So let's just make a dot for the object, and this vector will represent the force applied to the vehicle. The problem is the vehicle has to actually move along the direction of this track. So, you know what? I would like my force to look like it's substantially different in size from the direction vector for the track. So let's just make it a bigger force, right? You get the idea? So we have a vector, let's call it u. No, let me call this one u. Keep things straight. And this one v. So v is the force being applied, u is the direction the thing moves. The thing we're actually interested in figuring out is a perpendicular projection of v onto this line. That is, we want to think about a line going perpendicular there and figure out what's the vector that starts at that initial point and whose tip is at the place where that perpendicular projection lands on the line, determined by u. We'll make sure it looks like that line keeps going, right? And we're able to find that actually pretty quickly using dot products. Let me just point out to you that we've got a right triangle sitting in our face right here. The right triangle has the angle between these two things right there. Let me pull it off to the side. Theta is in there. The length of v is the hypotenuse of that triangle, right? I don't know what this side or this side is, except, well, wait a minute, I do, because I know trigonometry. This side is the cos of theta times v. Or rather, the length of v. And that piece is an element that you see in the dot product. Remember that the dot product of u with v I can do it in two ways. I can do that thing where I multiply corresponding components and add them all up, or I can do this geometric interpretation. It's the product of the lengths of the vectors times the cosine of the angle. You see the piece I'm talking about sitting right in there? That's the one of the sides of our triangle. And that's this distance, the distance in the direction of u that v projects onto. Sometimes called the shadow of v, because if the sun was way up that way so that it was shining straight down on the line u, this would be the shadow. Right, but that's a scalar. That's a length that we're after. Still, to figure out how long this vector is, what's the magnitude of the force, that's pretty easy. That is, the number I'm looking for is just divide out by the length of u. So let me write this on the side. So the magnitude of the projection it's take the length of u out of the equation. So you get u dotted with v divided by the length of u. Very nice. So if I actually want to know what the green vector is, here's the trick. Figure out a vector that points in the same direction as u does and is that long. And what you basically need to do is turn u into what's known as a unit vector. Take u and divide it by its own length. Yeah? And then times it by this quantity. So this part turns it into length 1, forgot its half. This one turns it into something of length 1, and then multiplying by that quantity turns it into something of length, well, the length we're after. And I feel like I can do something more with this. I could certainly combine those and talk about the square of the length of u. Oh, that's actually kind of a nice thing to do. Yeah, let's do that. Kind of break lines here. This is equal to u times the dot product of u with v divided by the length of u squared. So normally when you find the length of u, you're talking about the square root of the sum of the squares. The length of u squared undoes that square root, and so it's an interesting thing to notice that you can write what's in the bottom there as u dot u. I've forgotten my hat on this one too. U dot u in the bottom, u dot v in the top, and then let's pull that u. That's the only thing that's still really a vector, right? These two dot products are scalars, so that's a scale factor, and that's a vector u. In other words, the amount to get the projection of v into the direction of u, you take the dot product of u and v and divide by the dot product of u and u. It's kind of cool that you divide by the dot product of u and u because, the point is that you don't really need to have, no, that's not a way to say it. Should you have any impact on the result of this? Really, no. I mean, I get u is just there to tell me what direction the track goes. U could have been this long or it could have been real tiny. As long as it faces in that direction, it's good. So we're basically dividing out by the length of u in such a way that, now the thing we're producing does not depend on the length of u. I just went and referred to the book, and it's a little unfortunate that they have an explanation of this whole thing with the roles of u and v switched. That is, u would be the direction of the track. No, I think I just said it wrong again. V would be the direction of the track, and u was the original vector. But hopefully you'll be able to understand that. So There's notation that we should learn. We write proj with a subscript vector of another vector. So the subscript vector is the direction in which you're projecting, or the direction onto which you're projecting. And so that means the vector in the direction of u, dang, I just said it wrong, in the direction of v, that you get if you project u into that direction. I'm sorry, this takes a little while to write out. Right, so projection into v's direction of u. This thing is a vector quantity. It's the vector in that direction. There's also a way to refer to just the size, and that's called the component. So the component in v's direction of u, that would be the size of the projection vector. So I think I'll end this lecture by just giving you a brief example of using these ideas of projection of a vector into the direction of another one in a physical setting. If you have probably one of the simplest machines there is, it's called an inclined plane, and it basically is a wedge or a triangle. Okay? If you have such a thing, it's possible to move rather slowly up the length of this thing and raise through a small length. And they believe this is roughly what people did back in ancient Egypt to get those heavy blocks up on top of the pyramids. They construct these inclined planes and then get like thousands of dudes together to push on the rock to get it to go up the plane, but maybe more than thousands, I don't know. They had slaves, so they could do a lot of that. So let's just keep ourselves to the realm of non-Egyptian world here. There's some block on that plane, and it's got a force of gravity acting on it. Let's say it's got mass m. The force of gravity then is straight downward, and it's at 9.8 times m in size, but it's directed downward. Okay? So if you write it, I'm thinking of this as just in the xy plane, so any z component is 0. Although if we were really talking 3D, we would make this be the xz plane, I suppose. Anyway, I should put that on here. Here's y, this way is x. So this vector is just a 2D vector whose length is 9.8 times the mass. In other words, it's got no component in the x direction, and it goes down 9.8 times m in the y direction. Let's make this mass be something real. How about we make this mass be 20 kilograms? Right? Then that 9.8 times the mass becomes 19.6. Guess I better get a calculator here. All right, so what did I need? 20 times 9.8. Probably shouldn't have needed a calculator for this. 196. That's the force of gravity, or that's the vector that corresponds to the force of gravity applied to this mass. Right? Now here's the problem. The mass, because of this plane underneath of it, if it's going to move, it either moves upward or downward. Of course, if we only had the force of gravity acting on it, it would try to slide back down the plane. In fact, there's two vectors that we're interested in. One is the vector this way in the direction of the plane, and the other is the vector this way, which is normal to the plane. Now you can see that I've probably drawn this one just about right, but this other one is much longer than it should have been, if you're thinking about projections. So what are these two guys? This one is probably the easiest to deal with. What's a vector in the direction of the plane's surface? That thing is called, well, what is that called? This is known as a normal vector. I'm not sure what we call that one. But anyway, it's the projection thing. So if we can just figure out a vector that gives us the direction of the plane, we'll be all set. I didn't actually specify what the plane was, but let's see roughly how long is it compared to its height. Let's call it 4 to 1. Let's call this 1 and this 4. That means we can get a vector in that direction. I'm going to draw it up here. Its components will be a -1 in the y direction and a 4 in the x direction. So it's 4, -1. Right? So there's a vector in the direction of the top surface of that plane. And this red vector here is the projection of our force vector onto that direction. All right. I feel like I want names for these two things. Let's call this one F for force, and this one D, maybe, for direction. So the little red vector that I've got drawn right here is the projection onto the D direction of the force F. And how does that work again? The direction of it, it's in the direction of D. And the magnitude of it, or sorry, the appropriate scale factor is the dot product of D and F divided by the dot product of F and F. That is, it looks like D dot F in the numerator and F dot F. I am definitely wrong. D, projection into the direction of D should not depend on D. We're dividing by D dot D. D dot F over D dot D times the actual vector D. Yeah, that'll be correct. Okay, so can we do all this stuff in our particular setting? D dot D is 4 times, well, it's a, I keep picking up the wrong pen. I'm going to lay this one aside so I don't do that again. Get quite the stack of pens for recycling when this semester is over. D dot D, that is going to be 4 times 4 plus -1 times -1. Which is just 1, right? So this is 16, this is 17. Okay. D dot F, where can I write that? Let's do D dot F here. That's going to be 4 times 0. Well, that's not very exciting. 4 times 0 is 0, plus -1 times -196. Okay, so it's just positive 196. So the vector we're after goes in the direction of D, but it's scaled by this number divided by that number. Projection into D's direction of F is equal to, let me write it down. It's 196, that's the dot product of the two of them, divided by 17, that's the dot product of d with d, and then times the vector d, which is 4 comma minus 1. Does that turn into anything nice at all? I can see there's a negative 196 over 17 in the y coordinate. Is 196 divisible by 4? It seems like it must be. So that's 49 over 17 and minus 196 over 17. Now, how about the other direction, the normal component? I should mention physically what these do. That vector is what's trying to drag the thing down the track. This vector is what's preventing it from dragging down the track. This vector determines how much force is applied between them, and the friction that the block experiences is exactly proportional to that normal force. So the higher the normal force, the more friction. And if the frictional resistance is greater than the tendency to move, the block will stay put. You know, you've probably seen that plenty of times. An object that's on an inclined plane doesn't move, but if you increase the inclination a little bit, it will. So how are these things related? We found one vector, we had the other. Do you see that the two red vectors sum is the black vector? So that may be the quickest way to get at what the other red vector is. Just figure out the number so that if you add it to this, figure out a vector so that if you add it to this, you get this guy here, you get f. Can we do that? Yeah, I think so. I've gotten a little bit ugly on this board, so I'm just going to take out the top half so we still see the numbers involved with the two vectors we're interested in. What I was just saying is that the normal vector plus the vector we just got, the projection in the d direction of our force F, has to be equal to the force F. The two red vectors add up to what was the black vector. So let's say the normal vector is unknown, but we figured out the projection. It's 49 over 17 and minus 196 over 17 has to be equal to f, which was known as well. That's 0 comma minus 196. So what could the vector's components be? Well, you can see that n's x coordinate has to be the negative of the x coordinate of that. Actually, might as well just re-express it in terms of what x is. That is basically solve this expression for x. I said x, but the variable is n. I'm not sure what's wrong with my brain right now. Okay, but it's the same thing anyway. We're trying to find this vector n, and we just need to subtract off this vector from both sides. So it'll be 0, negative 196, minus this one with the confusing fractions in it, 49 over 17, 17, and negative 196 over 17. And we're subtracting that 49 over 17 from 0, right? So you're going to get negative 49 over 17 in the x slot. What are you going to get in the y slot? You got a number, and then you're adding to that number 1/17 of itself. No, wait a minute. It's negative, and then we're adding 1/17 of it. So it'll still be negative, but it'll be 16/17 of itself. Or, you know, get out a calculator and figure out what this is. The size of this normal component is considerably bigger than the amount that projects in the direction of D. So I think this block would probably stay put on a 4-to-1 slant. I guess, is it possible I should illustrate this idea of sliding blocks to you? I think I've got something that'll work. My calculator here, if I set it on an incline like we had, about 4-to-1, it's not going to slip. But if I got to try to make sure I can catch it off the end. If I increase the tilt, at some point, I didn't catch it. It's okay. These things are sturdy. Let's see if it still works. Woohoo! Yeah. So well, that was amusing, I suppose. Anyway, that's it for today. I'll process this video and try to get it uploaded before supper time on Sunday night. So hopefully we'll all get a chance to look at it, and I'll see you tomorrow.